This morning's session is Fyodorov from King's College London, and he will talk about freezing transition in decaying burgers, turbulence, and random matrix dualities.
Yeah, thank you. First of all, I'd like to thank the organizers for opportunity to present, to make this presentation in this nice environment. Nice to be Newton Institute again. I decided to make this choice of the topic, although this is based on the paper, in fact, short paper, EPL, probably not much known in this audience. It's Europhysics Letters, so it's in fact it was quite short paper of 5 pages, but it's so much packed with material that even for me reading it, it's difficulty. So I decided it will be good to remind myself and maybe others what was there, because I believe there was quite a few interesting observations made on that paper at the level of physical rigor. So although it does not conform to recent developments, it depends of course of definition of recent, but probably 2010 cannot be classified reasonably as recent, but for future directions, especially from the point of view of rigorously verifying some of maybe in the end of the day all or falsifying the claims done in this paper, I think it can be interesting future development. So what is this about? So it contains a lot of words. I will gradually explain all of them, but let us start with definition of Burger's turbulence. Maybe not everyone knows what that. This is solution of Burger's equation. So Burger's equation, we start with, okay, I'll write it so we have a vector field V which satisfies the following equation. Okay, this nonlinear term, and then there is, okay, a viscous term. This is viscosity, a positive coefficient times Laplacian, and then typically one adds forcing, just some forcing term, but in the problem of Burger's turbulence, this forcing is set to 0. So what then remains? What remains from? I mean, since majority of people probably consider this is the most interesting part, so then the question immediately arises: what remains interesting of this problem? But still, we can impose various types of initial condition and then follow the solution. And this is what is done in the turbulence. So in this so-called burbulence, sometimes people call it, because it's not really, the model was proposed by Burgers himself. I mean, he thought that maybe it will shed some light on real turbulence, but it's not really the case. It's very interesting, but quite different model. Okay, this is not movable. Let me then leave it like that. Maybe only add what type of initial conditions we'll consider. So we consider random initial conditions, and basically this is specifying V of V the function of x, which is okay. In general, it can be in any dimension at time t equals 0 specified. And then we just follow development of solution from a given initial conditions. What I'm going to present will be a special choice of initial conditions. So first it will be special class of initial conditions, then it will be further specified to very special choice, but I will argue that this is a relatively interesting choice. But first, what is this special class of initial conditions? In fact, physicists played a lot with, I mean, long ago, in the last maybe 30 years or something, starting with work by famous physicist, astrophysicist Zeldovich, they played it, they tried to use it for understanding information of meta distribution in early universe and some other zillions of other applications. And in many of these applications pointed to interest in so-called scale-free initial conditions. And these scale-free initial conditions, okay, I will denote averaging or taking expectation with respect to initial condition with the overbar. So basically I also consider only Gaussian fields or eventually processes, since I will mainly will be able to say something explicitly about d equal 1. So from the very beginning I'll consider d equal 1, but if someone will be interested in my opinion what happens in higher d for similar problems, you may ask if or if I have time I will mention in the end. But mainly my consideration will be explicitly restricted to d equal 1 and scale-free, special scale-free initial conditions. Namely that, okay, v of x at initially, v at another point, okay, this correlation function asymptotically for large separation between x and x prime behaves as 1 x minus x prime to power k plus 1, where k is parameter which will play essential role in what we are going to discuss. In 1D there is no any restriction of generality if we assume that v initially, v at x t equals 0 is a gradient minus gradient of another function which is called potential. In higher dimension this is only a special class of gradient initial conditions, but in 1D it's general, and if it's gradient initially it will stay gradient, is easy to show. So one can also, I mean equivalently one, and even more conveniently one can specify psi naught then is called potential, and specifying covariance, we always consider mean zero Gaussian fields, but so we specify the covariance of this potential, and it's easy to see that it should be 1 divided by x minus x dash k minus 1. So physicists like to speak about short-ranged and long-range potentials, and calling potentials with decay faster than, so for k larger than 1 short-range and for k smaller than 1 long-range. And basically one can say that k larger than 1, basically psi of x, psi naught of x is a stationary, Gaussian stationary process. In particular, it always can be chosen. So this behavior is asymptotic for large separations, but for small separations, it always can be chosen with finite variance. Again, physicists call this short-ranged. And the case, so k larger than 1, short-ranged in physical terminology, or stationary Gaussian process. Now, for k smaller than 1 and larger than minus 1, it's easy to see that it's impossible to choose it to be stationary. One only can choose corresponding process to be with stationary increments, and like Brownian motion, for example. So this is called this long-ranged or stationary increments. In fact, it makes sense even consider k smaller than minus 1. Then one can only make already velocity to be with stationary increments. So this model with this type of initial condition, few cases were considered in mathematical literature, but in fact physicists have qualitative understanding of what happens for basically any k. So what maybe I just mentioned that 3 cases were considered so far in mathematical literature. K equal 0, which is basically when psi naught is like Brownian motion. And V then will be a delta correlated field. This case was considered. Then I think the case when velocity is, velocity itself is Brownian motion was also considered, and delta correlation when basically psi naught is white noise. This also. So these 3 cases, there are some rigorous results. For other cases, there is only qualitative understanding. So what we, by the way, what people usually interested and thought that it's basically the only relevant question is considering limit when this coefficient, viscosity coefficient, tends to 0. So when this coefficient tends to 0, so qualitatively V, then V as a function of x will be looking something like it. It's random, then it experiences so-called shocks or drops, then it again increases, then it experiences drops, and so on. So people were interested in finding statistics of this, how high it goes, then statistics of shocks, of separation between shocks. These are interesting quantities, but these shocks develop only literally when viscosity goes to 0. Otherwise, they are broadened, and also interesting question how this broadening depends on viscosity. But let me just give qualitative understanding of what people expect for just field V of xt, some general properties for various values of k. So for a long time it was general belief that V of xt, if you take it at a given point, then it for all times and for all x's, if just initially it's obviously by definition it's Gaussian distributed. It remains Gaussian distributed. This was first. Gaussian distributed, normal variable. And if it's Gaussian distributed, then if we're interested in just properties and in one point, one only should specify the behavior of basically its variance, right, locally. And then predictions are that it behaves as t to power minus 2 k plus 1 divided by k plus 3, as long as we deal with long-range potentials or with potentials with stationary increments. And for short-range case, for which in fact the first results were obtained for short-range case, this is believed to be the following behavior: t square root of log t. This is so-called Kida type behavior. Kida was the first, I believe, the first person who gave this result for short-range potential for k larger than 1. Okay, so this is what one expects.
Why do you expect it to be Gaussian?
Oh, no, it's just okay. There is no theorem on that. That's in fact I will try to, on one particular example, give argument that it won't be, but at least in one case. I don't know in general, but this was general belief in physical literature. I don't know any particular, strong argument in favor of that, but this was what people expected. So my goal today is consider precisely the case which separates these two, namely k equal 1. This is very special case and related with interesting, I would say, physics and mathematics. And what means k equal 1? It's clear that we cannot just simply take k equal 1 here. It does not make any sense. But one should appropriately consider. So our goal will be to consider and to argue that this is one of the most interesting cases and reach the case, boundary case between short-ranged and long-range, between potentials with stationary increments and stationary potentials, k equal 1, when really we would like to require that this potential behaves as a logarithm. I will write it -2. This coefficient is more or less arbitrary, is a convenient choice, divided by L in the range epsilon smaller than, okay, separation between this should be larger than epsilon and smaller than large KL. L can be considered as just an interval where we, an interval in which we consider solution of this equation. It's again more or less arbitrary parameter. And for smaller than epsilon, this should be this process should be regularized. This is a process with logarithmic correlation. And in recent, in the last decade, there was a great interest in these processes with logarithmic correlations from various perspectives and a great understanding of their properties. And in fact, okay, it's known that this cannot be considered as usual process. Generalized, in fact, it only can be understood as generalized function or distribution. But there is a well-defined theory behind this. I will mention maybe later on when we play with this. And in particular, there was a lot of interest in statistics of extreme values of these logarithmically correlated fields. And basically, what we'd like to claim that in this special, for this special choice of initial condition, this will be the main message, we argue that there will be non-trivial phase transition when we vary parameter viscosity. And we conjecture that this is the only case among all these class when this transition happens. If k is not equal to 1, there is no phase transition. Always a system will be in one of the two possible phases, but in this situation there will be critical value of viscosity, and below which we argue that, so above which we will argue that indeed distribution of velocity is Gaussian, but below it becomes non-Gaussian when we can, this is basically the nature of this, the simplest manifestation of this transition, but we believe that there is much larger picture behind it. Yeah. Yes. We will keep viscosity finite and consider what happens when we decrease it towards 0. We will see that we cannot reach 0 without phase transition on the way. And after, speculating about the nature of this transition based on our approach, we will predict also what happens at viscosity equals 0. Okay. So why this is, by the way, why this model did not provide a good model for turbulence? Because it's integrable. It's well known that by Cole-Hopf transformation you can just explicitly solve this equation, and we will use it. So Cole-Hopf solution Cole-Hopf solution can be written explicitly, namely v of xt is equal to -2 times this viscosity coefficient derivative of log of z of x in t which by the reasons will be clear in a moment. We will, Z, it's natural to call partition function. And Z of x in t is given by the following integral, is integral of, over variable y divided by some normalization factor, which will be of secondary importance for us. But nevertheless, I will write it explicitly. Then exponential minus 1 over 2 times viscosity. This is viscosity, nu. And then the function h, x of y, where h x of y is given by sum of two pieces. The first piece is just parabolic, is just x minus y squared divided by 2 times time variable t. And second term is our initial potential. So it's easy to verify that explicitly, just because it's explicit formula, that this provides solution to our problem. So it seems that the problem is solved, so we have this. But of course, the whole interest and non-triviality of random initial condition that we have this term in exponential, we have a random Gaussian term. And not only this, it comes under log, so if we take derivative, it will be a ratio of derivative of z over x to z itself, and this is our velocity field, and this is ratio of two non-trivially correlated random quantities, and the problem is what to do with this. So now immediate observation is why we and everyone else, not everyone probably, but many people call this partition function. It in fact resembles very much or equal to real, if one identifies 2 times viscosity with temperature, so if one just identifies temperature, parameter temperature, equal to 2 times viscosity, we see that this indeed takes the form of the partition function for, say, single particle in a potential given by this h. So it's exactly will be Boltzmann weight. So one can consider associated Gibbs-Boltzmann measure, and this is like playing simple variant of simple but not trivial variant of statistical mechanics in random potential. So, in fact, understanding this was our initial motivation, because before that paper and after that paper, we played a lot with statistical mechanics of a particle in a logarithmically correlated random potential, and we knew something about that, and we hope that it also will manifest as here. Now, maybe just a few words about this background of particle in logarithmically correlation potential. Probably the problem which is mother of all these problems is Derrida-Spon paper on directed polymers on trees. So basically, let me remind you basically what is this. Is just so consider just say binary tree. One can consider generalizations, and then construct attribute to every endpoint, so just for many generations, and potential at I would say is associated some sequence of random variables v1, v2, v2 to k if we have k branches, k generations, just associated by associating with every age independent random, say Gaussian for simplicity variable, just summing along the branch and attributing this sum a value v. Then it's easy to see that essentially these v's will be logarithmically correlated, although not in Euclidean distance but in so-called ultrametric distance, but this does not play essential role. In recent years there was understanding that really logarithmic correlations are very robust. Whether they happen on an ultrametric distance or in Euclidean space, of course, in the end of the day, for technicality plays an essential role, but many properties are inherited just from the fact of logarithmic correlations. In particular, one can build partition function z, which is sum over all, I don't know, I from 1 to 2 to k of exponential. Okay, physicists usually write minus 1 over t vk. Mathematicians, by reason not clear to me, always put plus here. I can live with this, but it's just, I mean, original Boltzmann-Gibbs will be natural to have minus. But of course, for random, I mean, it does not play any essential role. So this is z depending on this temperature, or an inverse temperature. Frequently one writes here beta. Inverse temperature is the parameter. And then one can consider corresponding free energy minus t log z. And ask what will be typical values of this free energy depending on I mean, how it changes when t changes. And there is an interesting phase transition, really, this freezing phase transition, where below some temperature, typical free energy, typical free energy, if I call m is 2 to k, then f divided by log m basically will go to, when m goes to infinity or k goes to infinity, to, if I remember correctly, something like t plus 1 over t, if in some normalization. Of course, it depends. I mean, one always can play with normalization, with variance of these variables in such a way that critical temperature for this interesting freezing transition will be 1. So when Tc is larger than 1, high temperature phase, and just 2 when Tc is smaller than 1. So this is called precisely, this is manifestation of freezing. So what happens? Free energy depends non-trivially on parameter t, but stops depending for t smaller than critical value. So it's, in this physical jargon, I think mathematicians also now use this. It freezes. It freezes to its value at critical point and remains constant. We will see that this picture on the back of our mind will help us to identify. Yes?
Why is it log m instead of m?
No, it's because correct thermodynamic variable is k. but doesn't matter. Okay, it's also related with if you consider this variance of this to be, it should be, if variance of these variables which we add is of order of unity, then it will be natural scale for extremal values of this process will be logarithmic in m. Okay, but this is of secondary importance, so let us try to treat, this was just digression, but it plays, this digression plays important background for what I'd like to discuss. And now back to our problem. I'd like to consider the probability density function for velocity at a single point. I call it P of v, which, formally by definition, I need to take Dirac delta function of v plus, I will introduce corresponding notations. Now, hopefully, you remember that I use overbar. Let me just check whether it will be seen in different color. Now I will need two different types of expectations. One is over initial condition, and this I call overbar. And there will be also second expectation value with respect to, from now on, I will use this replacement. I will call t to nu in order to use this analogy with statistical mechanics. So I will call this then partition function. And then I will introduce corresponding Gibbs-Boltzmann measure and expectation with respect to it. I will use angular brackets to denote. So what is should be put here, it's easy to see from the definition that it will be the following thing. I will call it T. This is Boltzmann-Gibbs expectation, where notation is that whatever I take expectation of in these brackets, this is just the following thing, is 1 divided by partition function, exactly Gibbs expectation. Integral dy divided by this factor, which I don't like to write, expectation minus h naught of y divided by temperature, these two new, and then whatever I need to find to calculate expectation. So this is basically introducing this Gibbs measure. Now, really, it's easy to show that if I'm interested in one point properties like the local distribution of local velocity, I can put x variable. Here it was hx. I can put it without any restriction to 0. Just problem will be translational invariant. So I put it to 0. So my h naught, so I h naught of y is now is just psi naught of y plus y squared over 2t. Okay, before okay, our goal is to calculate or to be able to say something about moments or just about the whole probability density in this form. This is complicated problem. So let us first consider auxiliary problem, which nevertheless already will shed the light on this and even will allow us to get understanding of what happens in the limit that Herbert asked about viscosity to 0 or temperature to 0 limit. Namely, let us really just consider, introduce this, okay, I will call it, don't know how to call it, probably disorder averaged Boltzmann-Gibbs weight or Boltzmann-Gibbs measure is the following object: 1 over z exponential minus h naught of y divided by z. Divided by 2. Divided by that. So this is now averaged over disorder. So this is the object. It's basically expectation over initial condition taken of associated Boltzmann-Gibbs distribution. It tells really which configurations of y, which points of y are weighted with this Hamiltonian are really supported under this measure for different values of temperature. And in particular, I hope that there is no doubt that when temperature goes to 0, we know that Gibbs-Boltzmann measure is supported on its global minima. So if I put plus here, it will be global maxima. but I mean, in the property formulation on global minima. So this goes basically to probability density for argmin. Argmin over y of h naught of y, which I call p naught of y. And this is okay. In physicist terms, it will be probability density for the position of global minimum of this random function h naught of y. And it's easy to show using the relation between v and this so-called thermodynamic average. It's easy to understand that this immediate knowledge of this function immediately gives us knowledge of probability density for velocity itself at 0 viscosity or 0 temperature, because this is, it's trivial calculation, just the same rescaled version of the same function. So if we are able to shed light on this, it won't give us P of V for arbitrary viscosity, but at least it will give us limit of zero viscosity, and then maybe learning something we will be able to shed light on behavior of P of V for general temperature. So how one now really we'd like to try to calculate this. This is standard difficult problem in statistical mechanics of disordered system. We have random potential, random part in our energy, and we'd like to evaluate something related with Boltzmann measure. Difficulty is mainly, I mean, technically due to non-trivial correlations between Z and values, I mean, in the way. So physicists know the only way, I mean, of dealing with this, and this is infamous replica trick, and this is what we do, because we do not know to do better. We hope that one day, because many problems which physicists treated in years using replicas now can be done rigorously by other approaches, and in most of cases replica calculations produced sensible results, and if they failed, we know why they failed. So it's dishonest but very powerful heuristic trick, so let us do it. Anyway, we do not know otherwise we should stop here. If we don't like to stop here, we just write. Replica trick is the following trick. I just remind you. 1 over z poses difficulty, but any integer power of z won't pose difficulty because it will be products of integrals containing exponentials of Gaussian random variables, and this is of course very simple to average. So let us write instead, write that this is basically replace 1 over z with z to n minus 1 with n larger or equal than 1, replace it here, calculate if we can. It's also not very trivial, but if we can, calculate this expected value of initial conditions for integer n, look, stare at the formula and try to guess what happens if we put n equals 0, which should give us back, obviously, 1 over n formally. So this is the replica trick. If one does this, one can perform this program, and then I just write the result for this. If I introduce notation gamma for 1 divided by temperature squared, just for brevity, then I have the following, that this trick gives us the following representation for Pt of y for arbitrary temperature. Not arbitrary, we will discuss. It's equal to formal limit of n tending to 0. Normalization factor, which I will discuss at the moment, I call it Sn of minus gamma. We will see it in the moment. Now, integral with, of the following, I will write it, 1 divided by n, sum of Dirac delta functions at y, sum from j equal 1 to this replica index n, and eventually n should be set to 0, y minus zj square root of t bracket closed, and I need to use yet another notation for the average. Let me see whether red color will be seen. I mean, is it seen? I mean, you can see it marginally. Okay, I will put these brackets. I will explain what these curly brackets now stand for. Curly brackets stand for the following measure. It contains Vandermonde determinant of variable. Integration here will go over variable z. Variable z from minus to plus infinity. real variables that. Here will be factor product of I smaller than the zi minus the j, which is known as van der Monde factor, raised to power minus 2 gamma, where gamma is this. And then a further product of Gaussian exponentials, just exponential minus zj squared over 2 divided by square root of 2 pi of j from 1 to n and dzj. So this is, so how one should interpret this? So one should take this sum of delta functions centered at values of zj and integrate with this measure. This is a result of formal calculation for positive n's. But eventually one need to consider this. So this is normalization factor here is the same average where I just suppress this delta function. So will be integral of this. These integrals are very well known in random matrix theory. They are known as and beyond, because these are basically famous Zelberg integrals. So this factor is known explicitly. Now, how one should interpret then ratio of these two? It's easy to see that this is nothing else as the density, formally, the density of eigenvalues of so-called Edelman-Dmitriev beta ensemble of random matrices of size equal to the number of replicas, so size n, which eventually should go to 0. At parameter, okay, now what are these beta ensembles for those maybe a few who do not remember? Basically, in random matrix theory, instead of minus 2 gamma here, there is a parameter which is called beta. It's temperature of the associated Coulomb gas, if you like. Doesn't matter. Here we have negative temperature. You may even wonder whether this integral converges for integer n and whether it's well defined. Yes, it's well defined as long as gamma is smaller than 1, which is the same as saying the temperature is larger than 1. Look there. Temperature larger than 1. So, in that regime, which is equivalent to temperature larger than 1, this is well defined for finite n, but moreover, which is far from being trivial, one can, in some sense, one cannot evaluate this with this delta function. At least we do not know. This will be equivalent to knowing explicitly density of eigenvalues as a function of n and then continuing into n. This information is not available explicitly in the literature. What is available and what can be done is to calculate moments of this. Moments means under this measure, PT, calculate, say, expected value of y squared, y cubed, and so on. In fact, only even moments will be non-vanishing. By symmetry, one can show that all odd moments will be vanishing. But let me do, and then one can perform them using basically Jack polynomials and things like that. Known tricks in random matrix theory, and one gets a result. So let me write it. I will write it not for moments, but for cumulants. So if I define the moment m to l equal to integral pt of y to power 2l dy, then I can, from these moments I can build cumulants. And I will give you results for the first few cumulants. First non-trivial is second cumulant, which is just the same as second moment, in fact, if mean is 0. And this is given by t times, t is time, capital T is temperature. This is the result. Now, next one, which is m4 minus 3m2, standard cumulant. C4 will be minus t squared, simple expression. Now C6 is 2t cubed t plus 1 over t, and the last one which I give, although we have them up to 16, C16, but I give the last one because it's first showing something beyond what we see, minus t4, okay, 26 plus 6 t squared plus 1 over t squared. Okay, and so on. In principle, there are algorithms allowing them one by one calculating. We were able only, implement them on computer for, lower one can be done, by hands, but higher, it's more complicated. You need higher Jack polynomials. So, but you can do it one by one. And the main observation is as follows. All these cumulants, and this one can prove, this fact one can prove, all these cumulants will depend on t in such, we call it dual form. They depend, formally, if you replace t with 1 over t, they do not change their shape. And this is, okay, at the level of this, it's exact statement which one can verify using known properties of Jack polynomials. So, Jack polynomials. So, we claim that all cumulants, and therefore function itself, in fact remains invariant, but its only valid is t larger than 1. So what this invariance means is a separate issue to be discussed. But its form is such that if you formally take it and replace t with 1 over t, it goes to itself. And now look at our paradigmatic example for the freezing on the tree. You see what happened with free energy. It was in such a form, t plus 1 over t, and then it's frozen. So not only because of this example, but this is just the first example in the literature. But before that paper, Pierre and myself, we put forward a conjecture. Parts of it are proved, but not in full. So it still remains a conjecture and challenge to prove it in general. We put the following conjecture, that if one considers objects related with a partition function of Gaussian logarithmically correlated process and fields, and if the result satisfies this property that in high temperature phase it depends on t only in combination which remains invariant when you change t to 1 over t, then this object freezes and retains its value below t equal 1. All these objects simultaneously freeze and retain their values given at point t equal 1. So, although this integral is not well defined at t, it's not defined at all, it's divergent, even for fine then, for gamma larger than 1, or for t, which is the same, t smaller than 1, we conjecture that we know how to make corresponding analytic continuation and then retain the value. Okay, I'm approaching soft cutoff. So this is what we really do. This gives us then immediately access to by this relation to cumulants or moments of velocity at 0 temperature, and let me just write it here. So we write then v squared, if we just make this correspondence, is equal to 2t 2t for okay, viscosity equals 0. This is 2t, and interesting information is in the second v4 minus 3v squared squared. So cumulant, which tells us whether it's Gaussian or not, and this is not 0. Minus 1 over t squared, non-zero. So the corresponding, and this is for temperature equal to 0. So we see that at least at 0 temperature, this method predicts that field is non-Gaussian because its second cumulant is non-zero. Now, what one can do further? I'm just describing very briefly what was done after that. Okay, we found we found in fact a way to generalize this type of calculation to calculation directly of P of V. It's more complicated, and it involves very non-trivial information about these measures and these integrals. We found that very useful. There are some very nice duality relations, related or not, probably somehow related with this duality, but we do not claim. Really duality at the level of random matrix theory, which allows really to calculate and make analytic continuation n to 0 in quite a straightforward way. Because usually it's very difficult if you have, for example, at this level, you have sum of 1 to n. It's not clear how to perform continuation. Here, we managed to do it using some nice properties, random matrix dualities. And the result was, as a result, we found the following behavior. Above this critical temperature, T larger than 1, indeed, we found that the field V is Gaussian, and therefore very simple. But at critical viscosity, which corresponds to temperature equal 1 or viscosity equal 1/2, obviously, because T equal to 2 times viscosity. So at critical viscosity, what happens? Immediately below it and everywhere down to 0 viscosity, field becomes non-Gaussian. It has non-trivial cumulants. We have explicit prediction of the dependence of these cumulants on viscosity. We checked them in, I mean, as much as one can go with numerical simulations. They're non-trivial, but our collaborator Alberto made a serious effort to convince us that we can see that type of behavior that is predicted by our formula, explicit formulas. Whether trust or not trust the simulations, it depends on your goodwill. Look at the paper and compare the figures with analytical predictions. But my message is that in this case is really there is something very interesting happening. There is a phase transition already at the level of 1-point statistics of velocity. Not correlations of velocity related to shocks, which is usual object which people look at, but really even in 1-point properties. And this is interesting transition. And now I'd like to mention that it was huge progress in understanding rigorously logarithmically correlated field from the corners both of probability and in fact interest in quantum in two-dimensional quantum gravity, this beautiful series of works starting from Duplantier-Sheffield and then accumulating to these magnificent papers by Kupiainen, Rhodes and Vargas, who managed to put on rigorous basis many things which physicists put forward as conjectures. In fact, some of our parts of our conjectures based on this duality conjecture that I mentioned were last year proved by Guillaume Remy, but not, it's just particular consequence of it, but it was rigorously proved. So I believe that now time is ripe of making these insights rigorous. Thank you. Yes, please.
I didn't get your complete results. So you have this z of xt, which depending on t and also depending on u.
Mm-hmm.
So presumably you have like a phase diagram in terms of t and u. So which region do you claim there?
Okay. Let me. I won't write. I will write just what I have, for example, for velocity. So let me just draw, for example, second moment of velocity as a function of, I'll write temperature, you can write it as a function of viscosity. Or maybe a function of doesn't matter. I put it on temperature, not to. So second moment as a function of temperature. There is critical, so the claim is for any time here t plays no important role. It's just a parameter you can set t equal 1 and it's absolutely general. Doesn't matter. Put t equal 1. T, small case t, this t, not temperature. Then viscosity is relevant parameter. So phase diagram corresponds to changing temperature. This is like in standard temperature phase transition or viscosity. So behavior of the simplest quantity already second cumulant will show non-analyticity, namely up to this point this is 2 minus t, just straight line, and then after this point it's 1 over it's 1 over t. Yes, they match at t equal 1, right? 1 over t and 2 minus t, they match. So you see that there is non-analyticity here, right? So this is what we are speaking about. This is phase transition. And at t equal 1, there is general phase transition in properties of this field. And cumulants change, and it develops non-Gaussian features. But even second cumulant, second moment, which does not know about whether it's Gaussian or not, already is meaningful, already knows about this transition.
So if you regularize your field psi naught and then compute pi y and then take epsilon, the regularization to...
This is all for regularization to, of course, in the limit when regularization, this epsilon goes to 0.
Okay.
This is, of course, okay. One should be accurate with that and discuss what the meaning of that. One should renormalize few things, but nevertheless, this is this well-defined limit in this sense. In the sense of this, I mean, corresponding exponentials of our process will be given by this now famous, how it's called, multiplicative chaos construction, and this well-defined procedure. And in this way, this is understood.
Yeah, I have a question.
Mm-hmm.
It seems that the model considered by Deda and Spohn is exactly the hierarchical version of what you were talking about.
Not exactly, because they do not have. It's grandmother of all these models, but it does not have parabolic confinement term, which plays, of course, for this particular problem important information. It just version. If you just take, where is my partition function? Is it somewhere defined? Should be somewhere defined. It's here. If you suppressed this term, it will be hierarchical version of this model.
And so, in that case, if you add that in the hierarchical version,
this we did not try. This we did not try to add. Maybe one can consider. I don't know. It's interesting idea. We did not try to consider discretization of burgers related to that. I mean, okay, I see your point, but we didn't try. I don't know. Sure.
I heard a talk recently by Ron Aharoni when he was mentioning that for these type of disordered models, there's kind of two methods. There's the replica, but there is also one where you run the renormalization group with random space-dependent couplings.
Okay, this is probably okay. Indeed, there are versions of physicists got understanding of this probably, roughly speaking, the same time mathematicians did. Maybe in some instances earlier, in some instances maybe parallel. But one of the most influential works was really not rigorous but very powerful renormalization group done by Pierre Doussal and collaborator, who showed that in fact in general logarithmically correlated model you should expect behavior reminiscent of this hierarchical structure in very precise form that corresponding generating function related with distribution of a partition function will satisfy famous KPP Fisher equation with traveling wave solution and all that. So this made the contact between these two, hierarchical world and usual world. Then it's now, I think, it's very powerful approach. It sheds light on what is going on, although, I mean, to compute some, or you can compute some tails, I believe, in this approach, but not the whole distribution functions.
If not, let's thank our speaker.